Hello from Bramley in the UK. I'm not sure what kind of greeting to use since we seem to have people on the chat from UTC +8 through to -8, so it's only really the Pacific Ocean that's missing. So welcome to the third webinar. I'm not sure 3 is enough to welcome back the frequent viewers, but no matter how many of these you've seen before, I wish you welcome today. So the webinars are intended as a supplement to Dyalog's user meetings and the local APL group meetings that we of course continue to attend. It's good to see on the second webinar we had more viewers on the first. That's a good trend, but we're also equally happy to see that we are getting a good number of registrations for the Dyalog user meeting in September. So the worry that some of us had that the webinars might discourage people from meeting in physically doesn't seem to be happening. That's great. We're hoping to reach more of you on a frequent basis. The interactivity, of course, is going to be limited. There is a chat room available if you look around on the screen. And anything that you write there is going to a moderator here, Richard Smith, who's sitting in the room next to me, and he'll be feeding questions to the presenters at appropriate times. The webinars are going to be recorded and available via YouTube. I know that's not the case for the last one. We had a few technical problems in that and we're making some adjustments. I hope that it'll be available within the next few days. So be patient if you're waiting for that. Our intention is to do these typically on a Thursday, about once a month. And we are aiming for a duration of we'll try to keep our presentations to 60 minutes or thereabouts. And we'll have good time for questions afterwards. A few practical tips if you haven't watched one of these before. You want to select the highest resolution available in your viewer in order to be able to see the live demos, which will be at fairly high resolution. It's quite easy to accidentally pause the stream, and if you just restart it, it's not going to catch up. You need to click on the live button if you want to resync. There is a 30 second delay on the feed. That shouldn't really matter unless you pose questions. You may experience it today at that point. Okay, so enough practical details. What we're going to be talking about today is the new language primitives that were in version 16. We did a webinar a month ago where I tried to cover all of the new functionality of version 16 in a single webinar. In hindsight, that was a mistake. And we've had requests to redo bits of it, go into more detail on various features. I'm not going to apologize for the quantity of new features, but perhaps the presentation could have been organized differently. So I think you can expect a series of webinars going into detail. If you have ideas for things you'd like to see more about, please let us know. So in version 16, we added we took 4 new symbols into use as primitives in the language. And we're going to go through each one of these. There are 2 primitives used as functions and 2 new operators. The Iota underbar is used for 2 functions called where and interval index. The enclose, or left shoe I think it's called, underbar, is used for 2 functions called nest and partition. The @ sign has been taken into use as a merge operator. And finally, the quad diamond is now something called Stencil, which allows you to apply a stencil function to a moving window. I'm joined today by John Scholes, who's going to be presenting about half of the material. These are not pictures of John and myself, as astute viewers noted also on the first webinar. These are not ducks either. These are Odin's ravens, who are the mascots of the webinar series. The story has it that they flew out into the world at the beginning of each day and gathered news that they brought back to their master. Actually, we look like this, but you'll be seeing us both live in a minute. So without further ado, I'm going to dive straight into the first symbol, which has been given to me to talk about, the Iota underbar. The monadic version of iota underbar is a quite simple function which simply returns the indices of the ones in a Boolean array. So if we look at this example here, we can see we have a 6-element Boolean array. I've colored the ones differently so that you can see the corresponding elements of the result. 1, 3, and 6. My index origin is set to 1 by default. Of course, this can be applied to the result of a comparison. In this case, we're asking what's the position of the e's, lowercase e, in the word Pete. The iota underbar also applies to arrays of dimension other than 1, so not just vectors. In this case, we're showing applying iota underbar where on a 2 by 3 Boolean array, which also has 3 ones in it. And the result of that is then a nested array containing the indices as 2-element vectors. The first one is in row 1, column 2. The second one is in row 2, column 1, etc. Obviously, the iota underbar, the where primitive, is closely related to pre-existing idioms in the Dyalog interpreter. So things involving /iota compress the index, the result of the index generator. And in this example here, we can see using the idiom omega compress iota rho omega, we're getting the same result, in fact, as if we had inserted iota underbar there. There are some small but important differences, at least in this version. The right argument to iota underbar has to be a Boolean, whereas the idioms would allow you to use the / as replicate. So that's a restriction. On the other hand, the iota underbar is more powerful in that you can use ranks different from 1, not just higher rank arrays, but it also works, gives the correct result on a scalar. I'm not going to demonstrate that to you here, but if you're curious, you can experiment a bit with that. And verify that if you take a scalar and you index it by the result that you get, you're going to extract all the non-zero items from the array. So why are we doing this? It seems almost frivolous. We have idioms to do this. They're already optimized. But experience from other array languages shows that having iota underbar as a primitive enhances readability and maintainability significantly, and allows you to write more powerful idioms that remain very easy to read as well and to optimize, like the examples here where we're using 2 trains. So where equals Pete, where equals E, returns 2, 4, and ZZ where found in FizzBuzz returns 3, 7. So that's the monadic version of iota underbar. The dyadic version is a function called interval index. And for interval index, the left argument needs to be a sorted vector, which specifies what you might call the fence posts, which then define one interval more than the number of items. So we can see here where the left argument is 10, 25, 50, 75. That defines 5 intervals where the first one goes from -infinity up to but not including 10. Then we have a series of intervals which begin at one of the elements of alpha and continue up to but not including the end of that interval. The end of the last interval, of course, being plus infinity. So if we search, in this example, 7 is before the first fence post, so the result is quad IO minus 1. It's index origin sensitive, and anything before the first interval therefore gets a 0 if index origin is 1. 10 is equal to the first post and therefore returns a 1. 17 is between the first 2, so we get a 1. And 77 is after the last fence post, the fourth fence post, and therefore gives a 4 in the result. Character data is also supported, so the characters define ranges. The first range in this example here is A, B, C, D, not including E, and so on. Other than that, it works in exactly the same way. And one of the interesting and important things to note about Iota underbar is that if the items in the right argument are all members of alpha, then the result of interval index is exactly the same as the result of the dyadic iota. So in this example here, where we use 10, 75 and 0, we see that we get exactly the same result, 2, 4, 1, with a train being used in the last expression there, iota match iota underbar, doing the two lookups and then matching the results. Iota underbar interval index is also very similar to dyadic iota in that it extends to higher ranks. Index of in Dyalog APL was recently enhanced to allow you to search for higher rank arrays. The search is for items that have rank 1 less than the left argument. So in this case we have a slots matrix, 2-column matrix containing the beginning of time slots, 9:15, 10:45, etc. And then we have an array of times, and we're looking them up in the slots to see which time slot each of the times corresponds to. 8:18 is before the beginning of the first slot, gives us a 0. 11:22 is in the third slot. And an interesting point to note is that interval index is a very useful function to combine with key. For example, if we have a 3-column matrix T of timestamps, on the left here we can see the 6 first and the 6 last rows of T, and some corresponding data X, which we can't see here, but that's a matrix with the same number of rows as T, or a vector with the same length as T. And then we create in U timestamps corresponding to the beginning of 5-minute intervals. We can see also the first 6 and the last 6 of those. Then if we use the interval index of T in U as the left argument to a key operation, that classifies all of our data according to these intervals, and we can easily summarize the data by 5-minute intervals using the first expression near the bottom of the screen. The one at the very end, we use alpha squad U, so we index into the intervals using the index of the interval, which is provided as a left argument to the operand to key, so that we get a result which shows the 5-minute intervals and the summary for the corresponding interval. So the benefits of interval index are that it makes classification or bucketing, as you might call it, of keys a very, very efficient operation, which I think it's true in very many applications that I have seen. This is in fact a very common operation, and often on very, very large arrays. So it's something that's going to simplify code and also make applications run a good deal faster. I think we have a number of beta testers who reported that this immediately provided very significant speed ups for core components of their applications. Okay, so that's it on dyadic iota. This might be a good time to take, on iota underbar, a good time to take questions if there are any. Maybe it's all clear this time. We did cover it. This is also one of the we can give John his 30 seconds notice and hold on for a bit. This is one of the simpler functions. It'll get more interesting as we go along. No questions? No. Okay. Over to you, John.
Okay, well, good afternoon. I'd like to show you a couple of new primitive functions and the at operator. So I'm going to share screen, and with any luck, you can see my screen here. Morten, can you still hear me? And can you see the screen? Excellent. Okay, so I'd like to start with a new monadic function, which is left show underbar enclose if simple. We often like to write a utility function, util, which takes a vector of words to process. And it's convenient for the user if we can also give the utility function a single word. So we often wind up with some code that starts like this, that says if the utility is taking one item, then enclose it before looping through the number of items. And the with enclose if simple, oh no. Okay. For enclose if simple, then we can, the reason that happened is because I highlighted a line and hit enter. So instead of the having an explicit if test, we can just loop on item in enclose if simple items, and that will work for both cases. And that's really all there is to say about this. It's a very simple but very frequently used facility. The next function is partition, and this is again very straightforward. The partition is defined to be identical to the APL2, the very nice APL2 partition, if quad ML is 3. And we've done this so that it brings this functionality to our QuadML1 users. So, for example, we can define a split function using this, and we can split character vector at blanks in a very simple way. Now I must remember not to hit return. So this is just using the APL2 style partition. Those of you who use QuadML1 will probably know this is a lot less simple to do this job in with a QuadML1 enclose. And I have to thank Gilgamesh for pointing out this very cheeky little fork, which does the same thing. So if you take this expression here and code it as a fork, you wind up with this. Coding. So very straightforward. Morten, I rely on you to ask if there are any questions as we go along. Okay. Now I'm going to spend most of my time with the at operator. One thing I should say in passing is that, of course, these functions can also take an axis, and they just behave as they have done in Dyalog for many years. So we can, for instance, split on columns. All right. So the at operator has been discussed in Dyalog for many years, and in the greater APL community for decades, and it's built on work done by many people, including Bob Benecke, certainly including Ken Iverson with his mask and mesh operations. And this is what we have in Dyalog. It's also interesting to point out that both K and J have similar functionality. So this is overdue in Dyalog. And there are two defining examples, which I'll explain. So the way to read this first example is to say multiply at positions 2 and 4. I'm using index origin 1. So the whole expression says 10 multiply at 2, 4 in the numbers from 1 to 5. And we can see that there's a selection of the second and fourth items to which the multiplication is applied. And the second, so in this case, the left operand of the at operator is a function, a dyadic function, and the right operand is a numeric vector of indices. In the second example, the right operand is a function. 2 jot residue tells me the odd returns a Boolean vector of the odd positions. So in this case, I'm multiplying where odd in Iota 5. And again, I hit enter without moving the cursor. Okay, now the multiplication, the first two examples used a monadic left operand, but it works just as well with a dyadic left operand. It works as well with a monadic left operand. So in this case, we're going to reverse the items selected at positions 2 and 4. And you can see just of those two items selected. Lcase is a function from defens.dws that just takes its character argument and returns lowercase equivalents for each of the alphabetic characters. So the next example says lowercase at positions where is a member of A, E, I, O, U, where there's a vowel. So lowercase at vowels in the letters of the alphabet. And we can see just the vowels have been lowercased. So it takes a selection of the right argument and applies the left operand to that selection. A very common use is of a left operand is to use left tack. And what this says is to ignore the right argument, make a selection, but then replace with the characters of the left argument. And this is equivalent to an indexed assignment. The previous expressions have been equivalent to a modified indexed assignment, and this is a straightforward indexed assignment. So this is the same as saying the Iota 5 is a vector indexed assign at positions 1, 3, 5 with ABC. And this form is used so frequently that there's a shorthand. If the left operand is itself an array, then it stands for the previous case with the left tack. So what this is saying is we read this as ABC at odd numbers in Iota 5, and we get the same result. So these two forms are equivalent. And this example shows you that in the previous example, the ABC was a 3-item vector, the same length as the selection. If I give a scalar, then this is scalar extended to fit the selection. So in this case, we have stars at those 3 positions. Now, there's going to be a short sermon. This is why are we doing this? And the reason is that I've been trying for many years to convince the community that functional programming and more generally denotative programming, if we can get into the mood of thinking in this way, it pays benefits. And what this means is that we think in terms of expressions rather than assignments and developing variables. So procedural, traditional thinking, we tend to think of programming as mutating variables towards a required result. We take the arguments and we massage them until we get the required results. Denotative, of which functional programming is a subset, develops definitions for the required result. And it's quite hard until you get the knack of this to distinguish the difference. And the reason for doing, one of the motivating reasons for doing @ is that it is the last piece of coding in, certainly with dfuns, where it replaces the procedural mechanism of indexed and modified indexed assignment. So what that means now is that all of the functions in the dfuns workspace can be written in a pure functional style. And part of my work at the moment is going through the dfuns workspace and replacing the indexed assignments, modified indexed assignments with examples of @ So if you load dfuns.dws and search for, if you do find quote @ quote, you'll find where how this has been progressing. And I'll show you an example if we have time at the end where this is different. It's turned out that it's not just a matter of, to do this translation, of doing a syntactic substitution. It turns out that it's a different mental approach to coding in this way. So it's taken me some learning to do this. I'll show you some examples. Okay, so in general, just to go to the syntax of this, in general, that we have an optional left argument, a left and right operand, and a right argument. And the right argument selects from the right operand cell selects from the right argument, and the left operand mod modifies that selection in conjunction with the left argument if it's supplied. And where cell can be either, as we've seen, a Boolean returning function or a numeric index array. So it's either Boolean function, or if it's an array, it's an index array. And the index array can either be a simple index of the major cells of the argument, or it can be nested reach choose indexing. And reach choose indexing has been in Dyalog since the very beginning. So we have those two forms of numeric indexing. And mod is a function of the left, of possibly the left, a function of the left and the selection from the right. So the selection selects from the right, and then mod is applied between this selection and whatever's in left, or it's the array value, which is a shorthand, as we've seen above. Now, here's a few examples with higher rank arguments. It's fairly simple to see what happens with vectors. This is PCO is a function, Roger Huey's function for prime number handling from dfuns workspace. And one PCO says, in this case, takes a 10 by 10 matrix of numbers from 0 to 99, and it tells me which of those are prime numbers. So I get a Boolean, 0 isn't, 1 isn't, 2 is prime, 3 is prime, 4 isn't, 5 is prime, etc. So if I take PCO And if I take 0 PCO, that tells me which numbers are not prime. So this example is going to say, take the non-prime numbers from this array and replace them with a dot. So this leaves me a nice array of just the primes with the non-primes dotted out. And it's a nice display because it shows you the sieve working. You can see that anything ending in a 0 is non-prime. If we come along to the 2 column, then 2 is a prime, but any multiple of 2 is non, and multiples of 5 are not. The even numbers are prime. So it's a nice visualization of the layout of some of the primes. Yes, yes.
So there's a question as to whether you could perhaps in layman's terms say a little bit more about the benefits of functional versus denotative programming.
Okay, let me come back to that then. Yes, that's good. There has been a movement mainly speared in the functional programming paradigm, where the programs that are made in terms of definitions, if you make a series of definitions and you test each of the definitions, then they are somehow independent, and they are more robust than if you have loops, and in particular goto. If we go back a little bit, when structural programming entered the arena, the goto was considered harmful. And the reason for that is people could get themselves in a mess by doing spaghetti code with gotos. And it was found that if you write with loops and if then else's, your programs were a lot easier to maintain and debug. And the functional programming paradigm took this even further. And what they say is that loops themselves can be problematic. We always make plus or minus 1 errors in loops. We go around one too many or one too few times. In particular, variables having state. If I say I becomes I plus 1, or I'm mutating variables, then that I get into trouble with referencing variables at different states of mutation in different parts of my algorithm. And an example is of a denotative. And to make a little joke, you can call yourself a denotative programmer if you pronounce the assignment arrow as denotes. That's all it takes to do it. But you'll find if you do that, if you say I denotes 0, that works. If you say I denotes I plus 1, then it's kind of meaningless. It clearly doesn't. So that keeps you honest. If you pronounce the assignment arrow as denotes, it keeps you honest. So thinking in terms of expressions which have no moving parts, there's nothing to go wrong. And the typical example of this is the famous expression for mean in APL, which is the sum of the items, or the mean of a vector is the sum of the items divided by the number of items. There are no moving parts in that. There's no looping, compared with a more traditional scalar-based language, and therefore it is more robust. There is much written on this, and mainly in the functional programming arena. I think that's really about most of the day. Does that? I don't know how the time lag is working. Is that enough to be going on with, or we'll run out of time? Yes. I bang on about this every time I get the chance of talking. I bang on about this using slightly different terminology. But it's surprising how many, including myself, we were all brought up in the traditional mental model. And it's very hard in the procedural mental model, and it's very hard to break out of that. We think in terms of a process going from one step to another step. Whereas the denotative model, I just think of free-floating definitions. As long as I have definitions for everything, it doesn't really matter in which time they combine. They just, as long as they're there, you can combine them. They're just there. There's no passing of time. They are atemporal. Okay, let's press hurriedly on then. Now, so what is it? Oh, this is a yes. So I'm dealing with higher rank arrays. So here I have a 5x7 matrix, and I'm going to reverse at 2 and 4. And what this does is to reverse major cells with a simple numeric index. This reverses major cells. So you can see alternate rows of this matrix have been reversed. And so it kind of reads like a zigzag. We read 1 to 7 and then go back again, 8 to 14, and then 15 to 21, and so on. Okay. And this, I don't often get a chance to use this word, but this is, the word for this is bostrapheden. It means writing in the same way that oxen plough fields. And there are some writing systems that write from left to right and then back again from right to left. Yes, spell bostrapheden. Yeah.
Okay, there's a question from Steve Mansour.
Yeah.
He gives the example 10 times at 0, 1, 20, 30. And I think the question is whether when the right operand is a Boolean array, how that's interpreted.
Yes, okay, that's good. Well, let me just go back up the screen. The way the interpreter tells is whether the right operand is a function or an array. So in this case, the right operand is an array, whereas in this case it's a function. And if it's an array, if you were in origin 0 and we said times at 0, 1, then that would be a selection of the first two items. If I put as a function returning a Boolean, it would be it would do the Boolean selection. Yeah. So for one example, I'm going to do this, but please remind me to. For example, let me modify this. It won't work, but this would be an index selection. But this, because it's a function, would be a Boolean selection. Let me do. Okay, so that would be a Boolean selection, and this would be an index selection with repeats if we were in origin 1. Yeah, so it's just whether the operand is a function or an array. Does that answer the question? Yeah. Okay. Moving on from bostrapheden. Okay, reach and choose. Dyalog has this. The at operator is implemented in terms of modified and indexed and modified index assignment. Under the covers, initially uses that mechanism, and therefore we have reach and choose indexing available. And therefore, with a numeric array, if it's simple, then it's selecting major cells. But if the index is nested, then it uses the equivalent of reach and choose indexing. So this is a reach indexing. Because this numeric array is nested, it's replacing the 1 and the 1, 5 item with an oblique with a transpose, and the 2, 2 item with a reverse in this example. And this is equivalent. If you just look at the manual entries on reach and choose, this you can see where these are. And then a very similar example, very strange example, instead of a right tack, and incidentally, I need a right tack here to stop these items stranding with these items to produce a 4-item right operand. I need to separate these so that this is operand and this is argument. Instead of using the right tack, if I use an up arrow, then because I'm in migration level 1, this will produce a 2x5 matrix. Up arrow is mix of hello world. And then I will have a, so this presents a matrix, and then this then becomes choose indexing. And this exactly the same example could be written using square bracket assignment. If you want to try that, you could translate this into square bracket assignment. But you can see the difference between reach and choose here. So we can use both reach and choose, and that's look in the manual for those.
So there's another question.
Yeah.
So it's related to this. If you have a right operand function that returns a non-Boolean array, how is that interpreted?
That will be an error. That's a good point. Thank you. Yes, that will be an error. And actually, that's a good point, because it's modeled, and internally it uses the Iota underbar function, the where function for that, and the where function doesn't like non-Boolean arguments. So it mirrors the functionality of where. So another way of expressing the Boolean right argument is where. A few more examples. So I'm going to make myself a 5x5 matrix. And so I'm going to put a 0 at the second and fourth row in M. There's one. These are just some examples to get a feeling for this. The selection in this case, the selection is a second and fourth row of M. So that is a two rows by 5 column matrix is the selection. So I could replace this with a 2-row 5 column matrix, and that is then commensurate. What I'm doing here now, this is where this stuff starts to take off, because this is unlike indexed assignment, which is a syntax. At is just an operator, and therefore it can be applied as the operand of another operator. So here we're saying put a 0 at 2s and 4s, rank 1 in M, and rank 1 in M, it applies to vectors of M. Therefore, this is going to put a 0 at 2 and 4 positions in the vectors of M, which is the second and fourth column. Okay, so the previous example put the 0 at the second and fourth row. If I do it rank 1, it's a column. So all of the other operators with the at can be combined with all of the other operators, such as each and rank and power, to give us combining forms. Here's 2 ats in a row. So what this is saying, the way this parenthesizes is here's an argument, here's a right operand, here's at, and then the whole of this is a left operand of this at. So at rows 2, 3, and 4 in M, I want to apply this selection, which is to put a 0 at 2, 3, and 4 columns of M. So this is selecting by combining 2 ats, I have I can select a square in the middle. And similarly here, this is using choose indexing. I could pick the corners of M and put A, B, C, D in. So these are just kind of fooling around examples to show you the versatility of this. I'm nearly out of time now. Yes, a good example. If this is, I've called this there's probably a better technical term, but in the matrix invert code, the Gaussian method for matrix invert swaps rows and of a matrix to align values. And here we can see this is just swapping the second and third row of M. And this is a very neat way of, it can be used in the Gaussian elimination algorithm, which is a nice test case for AT. And that seems to work.
Don't worry too much about time. You took some questions.
Okay. Okay. Now here's an interest. This is a model of an under operator, which is I think proposed as a future extension, and this is nothing to do with that. It just says the way this works is it takes two operands. It applies the right operand to omega, then it applies to the left operand to the result, and then it undoes the right operand. And so if we see an example of this, the way to pronounce this is at under transpose. So the under operator is doing a transpose of M. It's then reversing the second and fourth rows of the transpose and then putting it back again. So this is another way of reversing columns. If we had a primitive under operator, this would be another nice combining form with it. So this is the way to read this is reverse at 2,4 under transpose of M. Transpose M, do the reverse of the second, fourth column and untranspose it again. This is food for thought. I think we're running very close to the end of examples. Yes, this is just another one. Yes, for higher rank arrays, the Boolean selection is scatter point. So this 2 residue of M is a 1 wherever for all of the odd numbers. So this is multiplying the odd numbers in this matrix by 100, and you can see these are scattered around the matrix. In case, go ahead. Yeah.
So related to this.
Yeah.
So I think Yves is asking whether if there, in the example you've just given, there's 100, there's a scalar on the left.
Yeah.
What are the rules for conformance between the left operand and the Boolean selection?
Good. That's excellent. The rules are, and I'm not sure if I dare, or maybe I dare tell you. At the end, I'll show you an example.
I mean, the question includes a specific case. It's quote ABC. I don't know. Can you type something?
Yeah, let's see what happens if I do. Quote
ABC at, and then the function you have above, 2 with residue.
Yes, 2 with residue, yeah.
And then Iota 9, so that'll select not 3 items.
Well, let's see what happens to me if I do it. Iota 9. No, and what's happened there? That is 2 residue is no, because 2 residue, 2 residue Iota 9 gives me 1, 2, 3, 4, 5 items. So I think if I did A, B, C, D, E, that's okay. Okay, the rules are that in this case the ravel of the selection is presented to the as the right argument of the multiply. So it's got to be commensurate in that sense. Okay, so let me be brave. So for example, I'm not sure what would happen if I resume my, let's see. Okay. So to residue, what's happened to me? I've got a caps lock on, residue M. If I do plus slash comma, so there are 13. So I believe, let's go out on a limb here, that if I say, let's take the 13 take of quad A at 2 with residue M, where's your money? Yeah. And I can, let me again go out on a limb. Tell me, I've got about another 3 or 4 minutes of presentation after this. But one of the things I can do is copy defense trace. Ah, I can do that from within. Oh, maybe I can do quad CY. Did it? Oh, I see. Date notified. Okay, let's see. So if I do 2 plus trace slash iota 4. Yes, trace is a little operator that dumps out what's happening as it goes along. So if I'm tracing this plus reduction by iota 4, I can see the order it does it. Now, if I go back to this guy and do, what am I going to do here? I think what I want to do here is change this to the left, spelt left form. Let's see if that still works. And then I can do that trace. See what happens to me. Yes. So what I can see here is can you see my cursor moving here?
Yes.
Yes. This is the example at work. If I trace this, then you can see the selection from M is raveled, and it is this is the selection from M, and then this is presented to the left operand function with the left argument. So the short answer to the question is, for higher rank arguments with a Boolean function returning right operand like to residue, it is the ravel of the selection which is presented as the right argument to the modification. Yeah. Carry on. Right, now we'll see what happens to me when I hit enter. Oh, I think that's very good. That was it. So yes, so just one more point to make and I'll hand back. At the moment, a word about the performance of @. At the moment, @ is modeled on indexed and modified indexed assignment in APL, and we expect that this to improve as we see usage of @ we will pick off usage cases, popular usage cases to soup up. Some of that's already been done. For example, if I had a usage case, if I had already had a Boolean array B, it's not B, and I wanted to use that as the right operand, then if it's an array, I need to make it into a function to so that it's telling @ that this is a function. And this, for example, is already, it won't go to the overhead of calling a defun for doing that. These cases are recognized. So more and more cases will be recognized. So we would expect the performance of @ to increase as we find out. Well, if people start using it, it will. If everybody thinks it's a silly idea and doesn't use it, then it won't. But I believe and encourage you to play with it. That's all, folks. So back to Morten. Unless there's another question. Or you want to defer questions to the end?
Well, there was a question, I think, that are we? Yep. Where if you wanted to replace the occurrence of one letter by another, so you used an example with residue. If you just wanted to compare, say, replace all E's by F's, how would you write that? Just as the last example.
Oh, okay. This is kind of, I'm not very good at programming with people watching me.
I think it's just equals, a function that composes, say, E with equals as the right operand.
Would equals, would do it. I think that would do it, yeah. Or and we saw one where we said you could have is a member. So yes, I mean that would do it, yeah. So that's Pete. Well, let's have. Have I got how many S's there? Let's have S.
I don't see you typing anything at the moment.
Ah, I wonder why that is. Can you see it now?
Oh, there we go. Yep, you were just off the bottom.
Right. So that's an example of function applied to an array. So then I could do.
Yep, that's the answer to the question as I understood it.
Okay.
Okay, thanks.
All right, thank you.
Right, are we back? Right, thanks to John. Now it's my chance to tell you a bit about my favourite bit of version 16, actually the Stencil operator. We're close to the hour, the first hour. I know some people have tended to drop out after about an hour, but I'm glad we got all the way through because I think that's perhaps the most significant new primitive in terms of how it's going to change the way we write code, being able to move to a more functional denotative style. But my favorite is the stencil operator. It may not be that widely used in existing applications, but I think it opens up APL as a tool of thought and an efficient language for dealing with a class of problems that, although they may have been fairly straightforward to write previously, they haven't always performed as well as you would expect an array language to be able to do. So the stencil operator is an operator which, as its left operand, takes what we call the stencil function. So a function that's going to be applied to a moving window on the right argument. The right operand is an array which specifies the size of the window. So if we look at the example which is on the screen now, the function that we're applying is just simply enclose. The reason for that is to show exactly what the right argument is for each call to the function. And the window size has been specified as 3 by 5. So you can see that the function, the def enclose omega, has been called it's been called 20 times, with each time with a 3 by 5 array. And it's been called exactly once for each item of the right argument. Each time one of the items of the right argument is the middle of the argument passed to the stencil function. And at the moment the only option for items which are near the edge is that we pad the argument with fill elements for the data type of the array. So you can see around the edges we're getting a bunch of zeros in order to make it possible to always provide a 3 by 5 array with one of the items of the right argument as the operand. So here's a vector case stating the same thing again. We have Iota 6 as the argument. We get 6 results back each time we've passed a 3-element vector. we think, or I think, sensible window sizes are going to be odd numbers. In fact, there was a discussion when we were designing this function as to whether the right operand should be the number of neighboring cells that you wanted on each side rather than the actual size of the window. I can't immediately think of an example where an even window size makes sense, but we eventually decided that we would allow it. So as you can see here, where the window size is 4, it causes pairs of items to appear as the center of each cell, and you get one less function calls than the number of items in the array, because we don't have enough. We only have 5 pairs to be made out of Iota 6. The default movement is to move one along and then one down and then one plane if it's a 3-dimensional array. But if you provide a 2-row matrix as the operand, then the movement between or the movement of the center cell can be specified. So in this last example on the slide, we're saying window size of 3, but move 2 along between each call. So far, all the examples we've looked at have only referenced the right argument to the stencil function. In fact, a left argument is provided which tells you how much padding has been provided. So if you use alpha drop omega inside the stencil function, you can use that to drop any of the padding items without having to work that out yourself. So the green numbers in the bottom half of the screen, we're using a stencil function that returns just the tuple alpha and omega, and we can see that for center cells, alpha is 0, but near the edges we get a number 1 for the first one to tell us that there's a 0, 1, 0 at a leading 0 in the first cell, and there's a trailing 0 in the last cell. And now it's time for a demo. I hope the font size is big enough, or that somebody will poke me if it's not. Okay, so just to limber up, repeat a couple of the examples we've already seen. So I'm using enclose omega with a window size of 3 on a 4-element array. The sort of obvious and perhaps most widely used function for most common stencil operations is something involving a plus reduction. So in this case, we're doing plus reduction on window size of 3, very similar to doing a dyadic plus reduction at this point, except of course we're getting padding cells. And we've said that on all of the slides. Now, what do people use this for? Well, there are a number of applications, in particular in image manipulation, in neural networks, computational fluid dynamics, where it's common to apply a transformation to one of these neighborhoods, a stencil operation to a window that moves around. So if we, for example, we imagine this is an image, and we've measured these are the pixel values. We've got a diagonal going through an image. It's very clear and crisp, 1 pixel wide. Then a typical blur stencil would be something like this 3x3 matrix, where you can see we've computed something which has the highest value for the center cells, and then it has numbers that get smaller the further away you get from the center of the matrix. And if we apply that, well, it's important to note the blur has a sum of 1. So if we apply it to a region, it's going to weight things and should, on average, give the same density to a region. If we're going to be applying these weighted stencils, and we're going to do a number of them, a number of examples that now to show typical image manipulation operations, rather than simply doing the plus reduction of the window, we're going to multiply the window by a stencil. They're all going to be 3x3 stencils. And then we're going to sum the result of doing that multiplication. So it's a weighted sum of the window. So plus reduce stencil times omega, and applying that to window size of the shape of the left argument. We're going to be passing in various stencil matrices as the left argument. I need to rename that or define that as a global name inside the outer defun, so I can refer to it in my operand function to stencil. Right, so I store this as stencil, and then I do multiply each of the items by that stencil. And I call it apply. So if I apply blur to that variable called diagonal, we can see that it has been blurred. As we move away from the diagonal, we're getting a smaller and smaller contribution from the diagonal due to applying that weighting. So blurring is a very common image manipulation operation. If we start again, I'm making a variable called box, where I started out by something which was all zeros or sixes, so a very sharp image of a box in the middle of a table or something like that. And then I apply the blur, I get this fuzzy picture of a box here, where you can see that where the original box was, we have quite large values, and then we have a fuzzy region, and then right out at the end we didn't get any contribution. The opposite stencil operation in image manipulation of the blur is of course to sharpen or to detect edges in an image that has been blurred. And it turns out that you can do that using one of these stencil multiplication, weighted multiplications as well. In that case, there are very many different types of these matrices with different weights depending on what kind of image you have, what kind of edges you're trying to detect, and so on. This is a very classical one where the numbers sum up to 0, so you've got an 8 in the middle, and then you've got 8 minus 1s surrounding it. And if you think about what that means, if you apply it to an image, what it's going to give you is a very small number if the region is fairly homogeneous. So if the pixel values don't have any big changes, then because the sum of the weights is 0, you're going to get a small number. Whereas if on one of the sides, or above a row or a diagonal next to the center pixel, you have very different values, then you're going to get a number which is very different, which is much larger. Sorry, it may be positive or negative, but it's going to be much larger. So if we apply this to the box, then we can see that we've got, unfortunately, because we're padding with zeros, we get some odd numbers near the edges. But basically you can see the contour of the box here. And then what you would typically do, you might need to play around with it if you're using Photoshop or something like that. You'd have various knobs that you would twiddle to find out what was a good threshold for the operation that you're doing now. And then you can see that we're now able to work out roughly where the box originally was in a blurred image. And then the final example before we start playing with some, wrap up by playing with some actual pictures, is this matrix here, which some of you will already have recognized based on the name. It's the glider from the Game of Life. And Conway's Game of Life is defined using these 4 rules, which make statements about whether you get a live cell in the next generation based on whether there are any neighbors and whether the cell itself is alive, trying to simulate ideas like overpopulation, underpopulation, reproduction, etc. It turns out if you sit down and turn those into numbers, if you define something where all neighbors are weighted by 2 and the center by 1, and you could reverse those as long as the center is different from the neighbors, then you can define the Game of Life using a rule like this. Simply say, apply that thing to the 3x3 windows, and if the result is either 5, 6, or 7, then you have a live cell in the next generation. So if we take the glider and apply the life function to it, it works. And if we write a little tool to visualize it, indexing character vector by the result, we can see the glider moving, and we can see that the glider indeed does, after 4 generations, resume its original shape, having moved slightly down and to the right. So the game of life is also a stencil operation, and if we look at the classical YouTube game of life, which is the last expression there, we can see that it's become a bit shorter. But I think more importantly, it's an expression that's easier to comprehend. Once you've got used to the idea of stencil operations, that first line is significantly easier to understand, and I think also easier for the interpreter to optimize, or a compiler to optimize, than the bottom expression. Though, if you're interested in the performance of this, you should look for a blog post by Roger Huey, which should be released soon, where he looks at various ways of writing this. And unfortunately for the stencil operator, we have a young man called Marshall working for us at the moment, who has souped up the Boolean operations something frightful. And so stencil is actually having a hard time beating that last expression at the moment, but we might get there. Okay, so wrap up with a bit of actual image manipulation. A long time ago, my daughter, while she was very young, used a tool called Microsoft Paint, which I believe is about to disappear in the next version. No, it's been... Really? I heard that Microsoft was going to get rid of it, but maybe by popular demand it's been given an extra lease of life. Anyway, I don't remember how old she was when she made this drawing, or whether it's a self-portrait or picture of me. But anyway, she drew this thing. And if you create a bitmap object, as I have done here in Dyalog APL, using the file with the name that she gave it, a very appropriate name, with 4 exclamation marks, we can read the C bits, the color bit data out of it as a 88 by 87 matrix, because that's the size of it. And yellow in RGB is 255 to 550, and therefore I can zoom in on a little part of it by setting, I should have used @ here, sorry John, I didn't have time to adapt the example. But that's a little region we're looking at, and just show you that if we can use 256 encode to separate the RGB values into a 3-dimensional 3 by 88 by 87 matrix. And if we index out that little region there, we can see that there's red, the red of the tongue, and there's the green and blue making the turquoise of the pacifier, I guess it is. So we can easily extract these bits into APL arrays. If we then define a function called blur, which just applies that blur stencil to an array, then we can write an expression where we apply blur each to the enclose rank 2 of that 3-dimensional matrix. So we blur the red and the green and the blue colors independently. And then if we take the result of that and do a 256 encode, we can assign it back to the cbits property of the bitmap, and we can immediately see the array being blurred. Now unfortunately you can see that round the edges, because we're padding with zeros, we get some slightly strange colors. So it would be better to define a function called blur, which actually drops off the you can see there's an n drop minus n drop here, where it's computed how much of the image becomes damaged by the operation. And then if we bring it back to the original, we can blur it, and we can blur it rank 2 to the power 4. So the advantage, as John showed with @ the advantage of using also rank instead of axis is that you can combine use of rank with power, and we can apply this thing 4 times and get a really blurred image. And here's an example that I actually used in a blog post when I was trying to control a robot a couple of years ago. If we write a function called edges, which applies the edge stencil to some bits and then again drops off the bits that you don't need, and has a default threshold of 7, it turns out is useful in this case. So if we take our original box that we looked at earlier, we can call edges box and get this result. If we create an image which contains, or form now, which is containing a picture that was actually taken by a camera on a Raspberry Pi robot, it's standing on a table and it's looking towards the corner of the table with a window and some curtains in the background. If we extract, we do a 256 encode again of the C bits and enclose them rank 2 and define 3 variables called RGB. If we then apply 12 edges each, so we apply edge detection to each of the colors and then we do an OR reduction of that, that gives a Boolean array which tells us where the edges are. And I'm now going to use the at operator to assign the color yellow at the indices in E, where E is 1, we're assigning yellow. So that'll color pixels yellow where the edge detection decided that there was an edge. And we then continue to do some manipulation. I hope this goes through the feed and we get this result here where the robot's taking a picture, running the edge detection algorithm, deciding how far it can move. There it decided it couldn't move at all. Here it's decided to cautiously move a little bit, and so on. So these are the kind of applications that interval index allows us. Okay, so time is running. It's worth pointing out that the stencil operator has high performance on a number of operations where we've looked at what we believe are going to be the most common operations. So the enclose, the plus, reduce, ravel, the multiplication by a matrix and comparison with a threshold. Those are all very, very common image manipulation. I think they're also quite common in neural networks and similar types of operations. We've optimized those. If you think you have functions you need to call that are not on the list, please call us and we'll look at providing. What we essentially can do here in many of the cases is to provide a version of Stencil or optimized code in Stencil that can do the computation in a single pass through the array, making it very, very competitive. Future extensions to Stencil, adding, at the moment you can only have fill applied to the cells. Obvious alternatives would be doing Stencil on a torus, only calling Stencil on full cells, and so on. Right, so those were the new primitives in version 16. Just to recap very briefly, we have the monadic, dyadic, the Iota underbar, where, which is added because it makes code more readable, it adds more power and simplicity. Interval index provides very efficient classification, bucketing functionality for big data analysis. Nest is a very, very frequently used utility function in writing application code. Partition is part of a plan to, in the long term, hopefully make it possible for new users of APL not to learn about migration level, which is there due to historical accidents. We don't have any plans to actually get rid of QuadML, but we would very much like to get rid of it from introductory documentation. The at operator makes it possible to write much more functional code, use a denotative style code without side effects, more parallelizable code as well is one of the side effects. And Stencil is a tool of thought for image manipulation, fluid dynamics, cellular automata, etc. Really opens APL up to, I would think, some new applications where we don't really currently at least have any commercial applications in that area. Right, so many thanks to Roger, who helped with the examples and comments on the presentations, and of course the design and implementation of interval index and Stencil in particular. As John mentioned, both AT and Stencil are work that builds on research done in the APL community for decades, maybe right since the beginning of time. People have been searching for functions called mask, mesh, cut exists in J and sharp APL, etc. And to many others as well, of course. Right, so that brings us to the end of the third Dyalog webinar. We're currently planning one more webinar in August, so slightly less than a month this time, to give us a bit of distance to the user meeting, which is September 9th to 14th. We haven't finalized the plans for the fourth webinar, but we have no less than 3 interns working for Dyalog this summer. And we're hoping that they'll be able to put on a bit of a show to show us the things they've been working on the 17th. So that should be fun. And we're not quite sure, I don't know whether Jason is nodding or shaking his head as to whether we'll be able to transmit live from Elsinore. That's something we're still thinking about, trying to find out whether the technical facilities will be available to us at the site. As usual, please send your feedback to webinar@dyalog.com. I'll wait a bit for questions, but I think Richard sent out a prompt a little while ago, and so maybe we've just covered it all and it's all crystal clear. We'll assume that anyway. So thank you for listening and watching again, and I hope to see many of you again on the 17th of August. And we should have both this recording and webinar number 2 up, watchable very soon. Thank you very much.